Welcome, everyone. Thank you for joining our webinar. Today we have Michael Clem of AMD and CEO of the OpenMP Architecture Review Board presenting on GPU programming with the OpenMP API.
All right, thank you. So hi, everyone. As Lizzie said, my name is Michael Clem. And before we actually talk about the introduction to GPU programming with the OpenMP API, I wanted to give you a quick overview of what the Architecture Review Board actually is, because I have to kind of advertise that organization. So the mission of the OpenMP ARB, that's short for Architecture Review Board, is that we want to standardize a programming language that is directive-based, based on compiler pragmas and in Fortran compiler directives. That is multi-language, so C, C++, and Fortran in this case. And what it should offer is high-level access to parallelism, so it should be easy to exploit the parallel nature of your machine. And we want everything to be performant, so you should be able to squeeze every bit of performance out of the system. We want this to be productive, so that you don't have to ponder too much about technicalities. And we want this to be portable, so when you move between different machines, you can carry your source code forward, and an OpenMP implementation on that other machine would work the same way as the machine you're coming from. And the strategy that we do for the OpenMP API is that we look at common approaches that are used in HPC applications and other domains, of course, throughout the industry. We look at those carefully, and then we distill them into this industry standard called the OpenMP API, so that we hopefully simplify a developer's life and make them more productive, performant, and their codes more portable. On the right-hand side of the screen, you'll see a bunch of logos. These are our members. So if you read through that, you will see that it's almost like the who is who of HPC. So we have almost all the US national labs on the list, plus several of the tier 0 compute centers coming from Europe and across the planet. And then obviously we have a whole variety of the typical hardware vendors and software vendors who are supplying HPC solutions into the market, so that we have a tight integration and tight collaboration between the user base and people who are actually implementing OpenMP and the hardware underneath it, so that it's kind of a holistic software stack that is exposed to the community. All right, so much for the ARB. Let's talk about the agenda, what I'm going to cover today. So first, I'm going to introduce the OpenMP device and execution model. I'm going to then talk about offload basics. So I assume that you have basic familiarity with OpenMP. You've seen a bunch of those directives before, and you probably already wrote like a simple OpenMP program, and that's kind of all you need to know. And we will carry on for starting with that and talk about GPUs. Then once we cover the basics, we will talk about how to actually exploit parallelism on a GPU. You'll see that there's some specific aspects to that. And then we will cover asynchronous offloading, where we want to talk about how the host threads can continue with OpenMP execution while the GPU is doing something else, also in terms of GPU execution. And then we'll wrap it up and have Q&A. All right, so introduction to offload features. I have prepared a running example. Consider this almost on the level of an Hello World program, but now from the HPC domain. And the example that I chose is SexB, one of the BLAS1 routines of your favorite math library. And so the blue part on this slide here, that's the stuff that I'm interested in putting on the GPU, right? And so quite naturally, if you already have pre-existing OpenMP code, you probably will start from an existing work-sharing construct that I have here in the blue part. The green part is actually not really necessary. Consider that as a little bit more code that I can show on the slide, so that the slide is not almost empty. Plus, you can think of this as being low man's performance analysis by taking, the current time running the kernel and then taking the time again to see if there's some particular speed up between host execution and GPU execution. All right, but technically it's not needed for the example. I just have it there as I just explained. The other thing, kind of a word of caution, don't do this at home, right? So this example is so simple. As I said, it's a BLAS1 routine that is shipped with almost any math library that I'm aware of. So there will be a tuned version for your system, right? So you don't have to roll your own, write your own SexB implementation, tune it for your system, and then, be kind of wondering about why you get less performance than a potentially highly tuned math library that is coming from your system vendor. So, the general advice here is just, if you have codes like this, use your BLAS library as a substitute and you get the performance benefits for free. But, as an illustrative example, it's still useful in this context of this webinar. All right, now let me talk about the device model. So with OpenMP 4.0, the OpenMP language committee introduced support in the language for accelerators and coprocessors. And I'm not specifically not saying GPU just yet, right? So everything that we will talk about will be useful in the context of GPUs, but that notion of an accelerator or coprocessor is much more flexible than being limited to just GPUs. And I'll come to that in like a minute. So the device model works like this. So there's a host for traditional multi-threading. That's the usual thing where you have CPU cores, where you have your operating system, and where a bunch of operating level system level threads are exposed to the programmer via OpenMP as OpenMP threads. Right, and then you can do everything that we had in OpenMP. You can do work sharing, you can do tasking, you can do SIMD and whatnot. Then attached to this are a bunch of accelerators, and they have to be of the same kind. So, for instance, all NVIDIA GPUs, all AMD GPUs, all, whatever GPUs. And you can have as many of those. They're assigned an ID from 0 to n-1 if you have n of those accelerators in the system. And the only restriction is that they have to be the same kind, so the same kind of architecture that the compiler can use. Now, why I'm not saying GPUs in this context just yet is because the accelerator can be anything, right? It can be anything where the host is sending a message from one of the host threads to this accelerator, send a command to compute something with that data, and then get the data back or get updated or computed data back from the accelerator to the host. Anything that fits that model technically fits the OpenMP device model. So this can obviously be something like GPUs. That could be something like the old Intel Xeon Phi coprocessor. It could be an FPGA. It could even be something like a quantum computer, or what I'm kind of often doing when I do a live presentation is we already gave every attendee like a small piece of paper with a small calculation on it, and kind of use them as our device for OpenMP offloading. So that's why I said the OpenMP offloading is way more general, and we will see a bunch of effects that this has on the design choices that the OpenMP ARB has made when it comes to the OpenMP offload features. All right, so we now have offload regions, so regions of code that we want to push over to, and from now on I'm going to use GPU as the main workhorse, to the GPU. And we need to have a mechanism to establish a data environment, so allocate some buffers or storage area on the GPU memory that we can put our data in. Then we can execute the code, and then we want the data back. All right, and the decision that the ARB has made, if you have an OpenMP target directive, and I'm showing the Fortran syntax here, C syntax would be #pragma OpenMP opening curly braces, closing curly brace. So if you have something like this, the data environment, so that the lifetime of the data on the GPU is bound to the syntactical scope of the statement. So that means if the statements open here, the directive opens the offload region here, the data environment comes into existence, and when we have the closing directive down here or the closing curly brace in C++, then the data environment is automatically destructed. Now, if you contrast that with CUDA or HIP or OpenCL, where you have to do explicit buffer management, there's a lot less boilerplate code that you need to write to make things work with buffer allocation and memory copies between the host memory and the device memory. All right, and the data transfers are also done at the curly braces. So when the data environment comes into existence and we have a data movement clause, the data is moved over, and when we destruct the data environment, the data is coming back from the GPU again. And let me illustrate that with a short animation here. So we have host memory where we have allocated some arbitrary data called A. So the programming language level syntax for that is identifier A. It has a certain pointer ABCD. That's the virtual pointer that you see as a programmer inside your program when you attach a debugger to it. And now when you do a corresponding map clause with an allocation request for A, the OpenMP implementation will allocate enough memory on the device to store A completely, right? And that pointer, that buffer will now have a device-specific pointer that is only useful on that GPU, indicated by this EF12. Then there's another map clause which ships the data over. So map2 is the command to OpenMP to move the data contents of A in the host memory over to the memory we just allocated on the device memory. Then we can call some computation on the device. We can update the data. And then when we do a map from, we get the data back from the GPU, and it's moved over to the original storage location on the host memory. All right? Obviously, while the GPU is working on that memory, you shouldn't be looking at the host memory. And conversely, before you move data over to the GPU, you shouldn't do anything with the device memory because it may contain some arbitrary garbage. And then, when I said when we reach the end target down here, what will happen is that OpenMP will clean up after that offload region and release all the device memory that was claimed for that particular code region. All right. For those who are watching this webinar offline as a video, I'm going to pause this slide for a few seconds so that you can pause the video and read up on the syntax. All right. Now let me talk about what this means for SexB. Right? So, this is the original blue code that I wrote with an OpenMP work sharing construct. And so what I want to do now is I want to send it over to the GPU, and what I do is attach an OpenMP target pragma in front of it. That's all I need to do. Everything else supposedly is done by the OpenMP implementation, and we will now talk about the specific details about what is going on. For the sake of saving you to Google search, down here for a bunch of compilers, I have the compiler options. So, if you look at Clang, there's the compiler options F OpenMP to turn on OpenMP support, and then you can use a target selection option to tell which target triple is the destination architecture. If you look at the AMD compiler, we also use Clang. It's very similar, except that we have a compiler flag called -offload arg, where you can say, for instance, GFX 908, which corresponds to Instinct MI100 generation GPUs. All right. Now, with this in mind, right, what we want to happen is we are in an OpenMP thread coming in here. It will encounter the target region. Control flow plus its data has to be sent over to the target device, in this case our GPU. And then at the end of the loop, down here where the offload region ends, control flow and some data is coming back from the GPU, and the encountering thread who was sent over to the GPU has come back and continues to execute the green part down here. All right. Now the question is, what happens to the data? Right? I don't have any map clauses here that I was showing earlier on an earlier slide. So what I have to do is I have to add clauses, map clauses, right? And the truth is the compiler has to be smart enough to cover the most important cases for you. And we will see a bunch of cases where you actually have to add your map clauses yourself. All right, so what the compiler is supposed to do is it has to look at the code inside that offload region. It has to identify all the pointers and data elements that you're executing on as part of that offload region, and it has to find their definition. And so in this case, I declare X and Y to be local stack-based arrays, so the compiler can actually see the size information and the storage location of that array through the pointer. And so what the compiler now knows is that Y is an array of size as Z, right? And what it will do for you is it will add a map clause, and I put it in a quotation mark, and you'll see that reason in a minute. So it will automatically add the corresponding map clause for the Y array to transfer it from the 0th element up to the last one, size -1, right? And it will automatically do a to/from, right? Because the compiler is not required to actually look at the usage of the data. It is only required to identify the data and then transfer it over before the offload region starts execution, and then bring everything back from the GPU, regardless of whether the kernel actually modified it or if the data is still the same as before. So we don't require that extensive compiler analysis in OpenMP at this point. All right, and the same will happen obviously for the X array, right? And there the transfer is actually not needed, right? The transfer back, I should say. So what the compiler does for you is it transfers over everything. So A is transferred over, X is transferred over, and Y, and then the arrays are coming back. The scalar A, this one down here, is not coming back. That's a performance optimization that we put into the OpenMP language. So scalars are just uploaded because the expectation is that scalars are usually used for constants or invariants or as loop bounds, and are not really, we don't really need to bring them back. If you want to, you then have to override that decision by the compiler using an explicit map clause. All right, and as I already said, X is not modified in the offload region, so we don't necessarily have to bring it back, but the compiler will still do it. In about 3 slides or so, we will see how we can avoid that. Now, if you care more about Fortran, you will see this, right? So this is the same code, same idea. So the compiler is required to move the data for the Y and the X array over from the host. It will find the definition of the data and the declaration of it, and will infer knowledge how much data it actually has to bring over from the host to the GPU. And Fortran is a little easier for the compiler to deal with, just because here the compiler has more knowledge, because if it's a Fortran 90 array, or a assumed shape array, I should say, the array has a so-called dope vector, so it carries information about what size it is, and it has a little more metadata attached to it than standard C, C++ arrays, where the array information is only attached to the type but not the object itself when you pass it around. All right, and then there's this orange box here saying presence check, right? So, and this is actually the reason why I put the map clause here into quotation marks. So what this actually means is that the compiler doesn't introduce the map clause, but it does something that OpenMP calls the presence check. So anytime there's an offload region that doesn't have map clauses for objects that are used inside that offload region, the compiler will determine if a previous offload region has already mapped that data. So there's already a device buffer existing for the data object. And then it will reuse that data buffer for that particular computation. The thing is, I told you that at the end of the target region down here, all data environments are destroyed, and I'll show you in a minute how you can create data environments that outlive a particular offload kernel and that can span multiple offload kernels and are not necessarily tied to the syntactical scope of such a kernel invocation. All right, just keep the word presence check in mind. All right, to fix up SexB, what we now can do is we can add the proper map clauses like I'm showing here. So 2 for X, we only need to ship it over to the GPU, and then to from for Y, because we need to read it once and then we're modifying it. So we have to bring it over to the GPU, and at the end of the kernel, we're going to bring it back. All right, so this is the behavior that we want for that kind of kernel. The other thing, or the other occasion where you need to have explicit map clauses, is when the compiler cannot see the exact definition of the data object that you're working on. Say you declare an array or you malloc some data outside of the SexB function. What the compiler then will see, and now I have a real SexB definition where X and Y are coming in as parameters are not declared on the stack. So here, it will find the usage of Y. It will trace Y back to its definition, which is float star, so a pointer to float data called Y, and that pointer is actually coming from the outside. And now the compiler doesn't see the definition anymore, and now it cannot tell how much data is actually stored behind that pointer, so that it cannot automatically add the map clauses or the corresponding presence check. And these are also places where you have to have explicit map clauses to tell the compiler how much data to actually move around for you when you do the offload. Again, if that were Fortran arrays and assumed shape, it would have the array descriptor or dope vector, and so the compiler can infer that from the object itself. If you are a Fortran programmer who uses assumed size arrays, then you're pretty much in the same land as in C, where the assumed size array is equivalent to a C pointer pointing to whatever data type that array is. And so the compiler is not able to tell that information unless you have a specific Fortran declaration where you add that information using a dimension statement. All right. Okay. The thing that you may rightfully observe so far, I didn't talk about parallelization. Right? And when you try this on your favorite GPU, you will actually notice that this is going to be horribly slow. And the reason for this is all we said to the OpenMP implementation is, compiler, move that code over to the GPU and run it there using that data environment. But what we didn't tell the compiler yet is to actually parallelize that loop. Right? So what this actually does is it runs exactly on one GPU thread. Right? And this is probably not what you want, because when you run only on a single threaded on a GPU, you're not really exploiting the capabilities of your favorite GPUs. So we'll fix that up in like a minute after we did a short commercial break. So one of the things that I would like to advertise is that the OpenMP ARB together with the community runs a whole variety of events, webinars like this one, tutorials, conferences, and whatnot. And so the prime venues, if you're interested in talking to us or other members of the OpenMP community, are the following events, the 5 events that I put up here. So there's OpenMPCon and the OpenMP users group. These are our developer conferences where people can just meet up and chat about OpenMP, and usually there's some good attendance of ARB representatives so that you can tap into the ARB via their presence, give your feedback directly to the ARB, and just engage with us to let us know what are your pain points, what are your wishes for OpenMP, and how do you feel about OpenMP as a programming model. Then there's IWOMP, the International Workshop on OpenMP. That's our scientific conference where we are gathering research contributions, publications, and have a workshop that is talking about OpenMP proposals, so proposals for new features, but also how OpenMP is used in applications and how it's used to do science in our community. And then there's supercomputing and international supercomputing. That's the venues where we usually have a whole variety of OpenMP tutorials. So this year at SC21, we have 4 OpenMP tutorials ranging from introduction to mastering tasking, advanced OpenMP programming, as well as GPU programming in a little more depth than I can present in this webinar. All right. If you want to know more about it, go to openmp.org. There's an events calendar where you can see what is coming next in our schedule so that you can sign up for this event. All right, let's talk about multi-level parallelism. So I already said this, transfer of control is sequential and synchronous. So when you do a target offload, there's exactly one thread, in this case, a GPU thread running and executing the offload region. The other thing that we designed into the language is that this is synchronous. So that means the host thread that encountered the target offload region is blocking until the GPU is done with the computation. And this is actually intentional. So we did not do a mistake when we designed it that way, but we had very good reasons to do so. So the idea is that we wanted to separate offloading, so controlling data allocation and movement of control between host and GPU, and how parallelism is created on the target device. And the reason for that is simple, right? We don't have just GPUs in mind. If you have a device that has a different approach to parallelism, like the Intel Xeon Phi coprocessor had, where you could actually use OpenMP tasking and get good performance out of it, you would overly confine OpenMP into a certain kind of supported architecture if you would have just a predefined way of how things are parallelized on something like a GPU. Right? So we want it to be flexible at the expense that now programmers have to explicitly create parallel regions on the target device. But on the other hand, we gain this flexibility that OpenMP can use not only GPUs, but also FPGAs or other offload devices that we probably don't even know about yet. Right? So in theory, you can combine this with any OpenMP construct, right? So if you have a device, like I was saying, that is good at tasking, you can actually use OpenMP tasking instead of plain old data parallel loops, right? But of course, in practice, there's only a useful subset of OpenMP features that you can use on a target device like a GPU, and I'll show you most of them that you need to get the first applications running on a GPU. The same, by the way, holds true for base language level statements, right? So what you absolutely don't want to do is you don't want to do I/O on your GPU, right? You don't want to work on a netcdf file as part of your GPU kernel. That's probably a bad idea as well. Or you probably don't want to do MPI communication while you're on a GPU. Right, so there's already a limited use of base language features, so having a restriction coming in from OpenMP is not too harmful here. All right, let's talk about SexB again, right? So I now remove the green code because now I'm gonna have enough code to show you elsewhere. So what we want, right, is something like this. Right? We offload, we create the data environment, and then we want to write parallel for SIMD. That's one of the OpenMP work sharing directives for multi-threading and SIMD execution, at least for a regular processor. And it is the same for a GPU. So when you write this, you should see some pretty good speed up on most GPUs already, because now you get something parallel executing in parallel on your device. Right? So what we do here is create the team of threads, a single team with a whole bunch of threads, probably thousands of them, and then try to execute that loop using SIMD instructions. Now the problem is that GPUs are actually multi-level devices. So some hardware vendors put in SIMD units. Like for instance, AMD's GPUs are organized in wavefronts, and inside that wavefront, you actually see a SIMD unit executing, right? These SIMD units then can then be combined into threads, maybe on some implementation, and those threads may be combined into thread blocks, right? If you think about OpenCL terms, you have work groups and work items. If you think about CUDA terms, you have warps and CUDA threads, right? If you think about AMD GPUs, you got the compute units and you got the wavefronts, which are then further subdivided, as I said, into SIMD units. So how can you exploit this? And let me just build it up and then kind of tell you that there's an easier approach. So let's take SexB and let's apply a manual code transformation on top of that. So what we do is we tile the loop into an outer loop and into an inner loop. So here we now have the I loop, which is now running from the beginning of the original loop to the size of the end of the original loop, but it's now no longer executing in stride 1, but in a stride that I call block size. And block size is determined to be the number of loop iterations divided by the number of teams that we're going to establish on the GPU. Think of this as being the number of wavefronts or warps or the number of work groups in those HIP, CUDA, and OpenCL terms. All right. So, and of course, I also assume that n is a multiple of the number of teams. So this actually adds up to be not ignoring some of the loop iterations. Okay. So what I'm going to do next is I'm adding a bunch of additional pragmas that you haven't seen before. So the first one is I augment target with the teams construct. So it's now OpenMP target teams to actually exploit those additional teams that I can now span across the multitude of wavefronts, warps, or whatever on your GPU. And I'm also adding the num teams clause back here to tell the implementation how many teams I want. So, for an AMD GPU, this could be something like a multiple of the compute units that you have in your GPU. And the other thing that I'd added is a work sharing construct called distribute. And what distribute does is it takes this outer loop running across the tiles in this of size block size, and it assigns each tile to one of those teams. Right? Consider that a regular work sharing construct now with the only difference that instead of assigning a loop to individual threads, it is now assigning that loop with a certain schedule to the number of teams that we created, so that each team is executing like 1 or 2 iterations of that loop. All right, and since I chose the block size to be multiple such that each team actually gets 1 iteration, this thing actually assigns 1 iteration of the outer loop to each team. All right. Then we assign the inner loop to the threads, right? So whatever that is, CUDA threads, slots in the wavefront for AMD GPUs, or work items in OpenCL terms. So now you will see the traditional parallel for SIMD that we had on the previous slide, but now it's attached to the inner loop, which is now iterating inside a particular tile to parallelize the computation on that tile and assign it to the actual worker threads on the GPU. And I added some color coding here. So red, yellow, green, and purple. And so you can spot those very same colors on this slide. So there's no need for you to do this manual code transformation, which obviously is doable for something like SexB, but not for a real GPU kernel. At least it's rather error prone and not very productive. So everything that I was showing on the previous slide, I can actually do by using target teams distribute parallel for SIMD by basically attaching all of those individual directives and stuffing them into a single directive to then do the manual code transformation I was showing previously, but now do it automatically. And in OpenMP for Fortran, this looks exactly the same. So here's your the SexB example as a Fortran version. Obviously, declarations omitted, but it's the same syntax. And correspondingly, there's an end directive that aggregates all those individual directives into a single closing directive. All right, again, for the syntax, just going to quickly pause here. All right. The main source of performance, if you already were programming for a GPU, I'm kind of preaching to the choir here, is to optimize data transfers, right? So if you have this scenario of host and accelerators attached via some communication fabric, in most cases, something like PCI Express or potentially in VLink or some other protocol, what you will observe is that when you look at the memory bandwidth that you can see on the different parts of the system, so usually you see something like hundreds of gigabytes per second for the host system, like something like north of 350 to 400 gigabytes per second are possible here. Then you have the bandwidth of the accelerator memory, so the GPU memory, that's usually in the range of terabytes per second. But then in between those two worlds, you get something like PCI Express Gen 4, which as of today, if it's a by 16 link, you get like tens of gigabytes per second, on the order of 28 to 29-ish gigabytes per second. So obviously you don't want to unnecessarily ship data around between host and accelerators or GPUs unless it's really necessary. So what we have to do is we need to avoid those data transfers. So first of all, we only need to transfer what is actually needed for the computation, right? So in the SexB example, I was optimizing already the data transfer of X by only shipping X over to the GPU, but not bringing it back because I knew that it wasn't changed as part of the offload kernel, right? So that was already one of the performance optimizations that we have to do here. And then the other thing that you can do, obviously, is you can make the lifetime of your data extend across a multitude of offload kernels, meaning you keep the data as long as the GPU as you possibly can and only bring it back when you absolutely have to, right? And I'm going to show you now how this can be done. All right, so the role of the presence check. So what this presence check does is, down here, I was already saying, the compiler adds a presence check for the arrays that you're using inside the target region and also, of course, the scalars. So there's this thing added which basically checks if somebody already allocated Y on the device, and if that is the case, then the presence check or that target directive will not transfer the data over again, right? And this is happening for everything that you use in the offload region. So how OpenMP does this is it maintains an internal mapping table of things that you had on the host and that you mapped on the target device. And it keeps that mapping from host pointer to target pointer to know if something has been mapped before, because then it has an entry in that presence in that mapping table. And if that pointer is not there yet, right, OpenMP knows how to transfer or needs to transfer it. Okay, and we can exploit that, right? So if we have a subroutine where we want to call SexB and we want to make sure that X and Y are already existing on the device, then what we can do is we can use a target data directive to explicitly map X and Y, pretty similar to what I was showing earlier. But now the data environment lives from this opening directive until this directive, and inside the caller, the callee, the SexB function, now the presence check up here for that target will determine that through that directive here, X and Y have already been mapped, so this target directive will not transfer X and Y again. So this can be used to do things like this, right? So you can use target data to allocate a temporary buffer. You can move data over, like in this case, A, B, and C, A and B, and then we have a computation involving C, so we upload C and we download it again. And then we execute a whole bunch of kernels. So the first one is a kernel to zero out TMP. Right? This is unallocated storage or allocated storage with uninitialized data. So we initialize it to be 0, and you can read TMP to be something like an accumulator in this case. Then we do a first compute kernel to take A and some, produce whatever version of TMP, and that now uses target. Right? Then there is the SexB kernel that you've seen quite frequently already. Then there's another compute kernel that also updates TMP, and then you do another SexB. This kind of example tries to resemble, even though it's meaningless, tries to resemble, something like a parallel CG running on a GPU where you have a whole bunch of array operations that you need to run for one iteration of the conjugate gradient method. All right, and then inside that zeros and SexB kernel, the OpenMP target teams distribute parallel 4 is good enough. With the presence check, it will detect that A, which now via this is pointing to TMP, to the allocated TMP storage, that this pointer has been allocated using that map clause, right? So it will not do a transfer of whatever is behind that A pointer, but it will recognize that there's already some storage allocated. And the same will happen for SexB. So again, the presence check for the pointer Y and X will determine that in the first invocation, this is corresponds to TMP, the pointer TMP and B, and it will determine that this data is already there. And the same for the second invocation where C and TMP are filled for Y and X. And so the presence check will also know that everything is just there. And you can, there's more how you can combine that. So here what I'm showing you is creating a target data environment on a particular GPU device. And what I'm mapping is an input. So there's an initial data upload happening. Then there's a first target that does some computation in parallel on that input data, producing a temporary array. And now here where my laser pointer is, we're actually back at the host, right? But the data environment is still up and running. And then some host execution will update the input array, right? Via the input pointer. And so what you can do is there's a directive target update to move data over and upload a new version or the updated values of the input array when you need it, and then you can launch a second kernel that then picks up the updated values on the GPU data environment and does the final computation. And it does a reduction into a scalar, and up here I'm actually showing you how you can bring the result back, so you can actually do a map from result and bring it back. All right, and when you execute this, the stripe on the right-hand side will show you where things are. Again, this is the syntax slides, quickly going through, but for you to pause the video. All right, time for our last commercial break. If you want to read about OpenMP, and if you read everything that I just told you, there's a whole bunch of resources how you can do this. Obviously, one is the OpenMP reference guide. So this is a condensed version of the OpenMP specification, just showing syntax, a mild amount of explanation around it so that you can use it as kind of a cheat sheet if you're unsure about how the OpenMP syntax for a particular directive should look like. And then there are our OpenMP books. So there's the Common Core, which introduces the basics of OpenMP and has kind of a focus also for teachers on how to teach it. Then there is the OpenMP specification book, where you can get a printed version of the PDF that contains the specification of OpenMP so that you have it in easy reach on your desk. And then there is Using OpenMP, the Next Step. That is a book that basically picks up and OpenMP 3 and explains the features in detail up to OpenMP 4.5. And if you're interested in how things work under the covers, there's high performance parallel runtimes, kind of a shameless plug because I'm one of the authors here. So I'm trying to crank up my book revenue here. So this basically explains how an OpenMP runtime system for a multi-core CPU can be implemented, and what the specific aspects are around, how OpenMP on this very lowest level interacts with caches and such. All right, asynchronous offloading. So far, everything that we did was synchronous. That means that the encountering host thread actually evaded the end of the target region before it continued. If you want to avoid that, there's the no wait clause, which then will turn a target directive like those down here into asynchronous offload regions. So basically the host thread, when it encounters the target, will launch the kernel and then continue whatever code comes in and launch basically those three kernels in sequence and continue execution. Now, the thing is, the way we designed OpenMP offload features is that we tightly integrated it with OpenMP tasking. So what this means is when you do the OpenMP no wait, like here, you actually turn the offload region into an OpenMP task. That's our OpenMP lingo for that. And that's why I actually put up this purple task here, because that is initializing data that one of the kernels actually needs to work on. And so the question is, since this is an asynchronous entity executing on some host thread, and this is an asynchronous entity executing on a GPU, how do you synchronize that? And the comment I made about integrating GPU computing with OpenMP tasking was made because since we do this, you get everything in OpenMP that is able to synchronize with OpenMP tasks is applicable to this as well. So in this particular case, what I'm showing you is you can have a depend clause that says for the first task, the purple task here, that it has an output dependency for A, so meaning it produces the value A, right? And I'm indicating the dependence graph that is resulting over here. Then the blue task down here, we can model that there's an input dependency on A because we are reading A, we're mapping A, and we're using it on the GPU. So this means now this task, the blue task, and the purple task have a dependency. Right? At the same time, we can say this GPU task is producing X, and we add the corresponding out dependency. And when we do this, we can model the corresponding output dependency for the red task, for the green one, and we get the resulting task dependency graph that I'm showing on the right side of the screen. And then when we want to gather everything, we can use a Pragma OpenMP task way to have like a task barrier. And what this now means to the OpenMP implementation is that the task dependencies will magically be used so that when some of the workers one worker has finished executing the purple task, it will kick off the blue offload region. Then this blue and the red offload region, they can potentially run on a different GPU device or run one after each other. They're not synchronized in that regard. And then the green task down here, the green offload region, will wait before it starts execution until the blue and the red task or offload region are finished. And then the task wait will wait for all the child tasks of the encountering thread. So that means it will synchronize and wait for all those threads to complete, basically meaning that it will continue once the green task down here has completed. All right, that's pretty much all I had to say about OpenMP offloading. So what I wanted to get across is that if you think about GPU programming, OpenMP is there to help you. We have a major OpenMP offload model that supports asynchronous offload and data transfers. On the last slide, I actually showed you how tightly OpenMP offloading integrates with OpenMP multithreading on the host, namely via the OpenMP tasking features. And there are a ton of more features, and I would really recommend to attend one of the OpenMP tutorials, either at SC or ISC. So there are more advanced features. So we have a full-fledged memory management API. So if you are unhappy about how the directives work, we have APIs where you can do memory allocation on the GPU, where you can transfer memory via memcopy operations, rectangular memcopies, and whatnot. We do have interoperability with native data management. So that means if you have OpenMP buffers that you allocated and you want to execute a HIP or CUDA kernel, you can convert and tap into the mapping table to get the corresponding CUDA or HIP device pointers out of OpenMP. In OpenMP 5.1, we added interoperability with the native streaming interfaces. So in theory, what you can do is you can ask OpenMP what is the underlying streaming mechanism that is used to execute something like a CUDA or HIP stream or HIP kernel, and then you can tap into that and then issue something like a QBLAS operation or ROCBLAS operation on that very same stream that also OpenMP is using. And of course, we also have unified shared memory support. So everything that I just said was assuming that you have a discrete GPU that is not able to share the host memory or the address space with the host memory. But if you do have a unified shared memory GPU, then we also have the corresponding feature so that you can use that kind of hardware capabilities. And with that, I would like to take a question, and I see that there have been already a bunch of those in the chat. So I'm going to pick them in priority order as they have been voted. So are there ways to get data transfer times host device within OpenMP region, or is that implementation specific? Yes and yes. So yes, it is implementation specific. So OpenMP does not have a mechanism. There's no way how you can tear apart, the memory transfer part of a directive versus the offload transfer part of the directive. But usually, most implementations that I've been working with have some implementation-specific environment variables or tools like RobProf, NVProf, CrayPad, I believe, where you can see that information and tap into the OpenMP implementation enough so that you can extract that information, even though you cannot do it from OpenMP. All right. Can we use NVIDIA GPU Tensor cores in OpenMP? That is a tough question for me because I'm not an NVIDIA employee. So that is probably a question that is best sent to NVIDIA to be asked. The general OpenMP style answer would be, in theory, yes, if you have a compiler that understands the code pattern enough that there is something like a matrix multiplication or a tensor operation that you're offloading, then in theory you could use it. But if the NVIDIA compiler is actually able to exploit that, I don't know, and so I cannot answer that question finally. I'm sorry about that. All right, then there's another one. What is the behavior of the target directive when no accelerator is available? Can I use the directive even on my local machine which contains no GPU? I've noticed the code is running with no errors. Yes, in fact, that is a good observation, and it's actually a true observation. So what OpenMP defines is what they called host fallback. So you can create that by two scenarios. So either, as in your case, you have a system where you compiled for, say, an AMD GPU, but you don't have an AMD GPU in the system. So in that case, the compiler will fall back and execute that target region on the host device, which basically means it will map it to your CPU cores. The other way how you can trigger this is there's an if clause. I didn't specifically mention it, but you can have a condition that is attached to the target directive. So you can, if this condition evaluates to true, you can specify that then the target directive should actually go to a GPU. If the condition evaluates to false, then you will stay on the host and you will use that host fallback to the CPU device or the host device. And so you could do something like, if you know that the data size is too small for the GPU to give you a performance benefit, you can just stay on the host. And what the compiler internally is doing, it's actually doing what is typically called multi-versioning. So it will generate a code path where the GPU is used, and it will generate the same code path, but now with host execution. And then when the host thread encounters the offload directive, it will determine if there's a GPU, and if the condition is true, it will do the offload. Otherwise, it will stay on the host. All right, the fastest memory available in NVIDIA GPUs is the shared memory in a streaming multiprocessor. I assume that AMD GPUs have something similar. Is there a way to explicitly utilize this memory? Yes and no. Yes, in the sense that either a compiler can be smart enough. So if you declare like, a local array that you declare inside a team's directive, the compiler can infer that it may want to map that to shared memory. No, in the sense that we don't have like a underscore shared underscore. The thing that we did though in OpenMP though is we have memory traits. So what you can do is there's an allocator interface that you can use, which basically lets you describe memory traits to the OpenMP implementation, and those traits then correspond to the properties of memory that you're asking for. So you can ask for something like high bandwidth memory, high capacity memory, close memory, far memory, and you can also ask for memory that is close to the team, which then an implementation that would be smart enough to recognize the trait could map it to something like the shared memory in an NVIDIA GPU. Right, but this is now then implementation defined and a quality of implementation issue if the implementation would actually understand that kind of memory trait and do the right thing that you're asking for. All right, then do we have support for FPGA? That is a difficult question. I do know that there are a bunch of research projects that have investigated how to compile OpenMP for FPGAs. I have heard that Intel One API should also have something similar. I'm not really sure because I'm not an Intel employee. So best is if you have a particular FPGA vendor, check with that vendor first if they have an OpenMP implementation. And if they do, check with them if they have an FPGA implementation also. All right, is there a way to transfer a pointer to function instead of a pointer to the data? A use case scenario is invoking a function received as argument in a pragma OM target region, and therefore the name signature of the function are lost at this point. Yeah, we do have basic function pointer support. They're probably not as extensive as you may need it for that use case. Unfortunately, there are not many details about what exactly you want to do. But OpenMP is perfectly happy if you're talking about C++ to map something like a lambda expression. That works at least in the most common cases. And as I said, we do have basic support for function pointers in OpenMP. So it may be that your use case is covered, but it may also be that your use case is not covered because I'm not exactly sure what exactly you're trying to achieve here. Is there support for adding OpenMP parallel target directives to a Fortran do concurrent loop construct? If not, will this support be added in the future? That is a good question. We are talking about this. We do have, in the Fortran space, we have two white spots on our feature map. The first one is obviously do concurrent. We are working on that. The second one is if you use array notations in a offload kernel, and you're tempted to use the workshare construct, you're not parallelizing across teams and threads, but only across the threads within a team. So we're working on having a construct in OpenMP 6. The potentially closest equivalent to do concurrent is the OpenMP loop construct, which I was not able to cover as part of this webinar. But we also have here's a parallel loop kind of directive, which doesn't really prescribe how the implementation has to be done on a GPU or on the host. And so even though we may not have do concurrent just yet, we may be able to nicely parallelize regular do loops, but I'm sure that we will have something in the OpenMP 6 timeframe to cover that. All right, and then there's a question, unsure if I understood this correctly. If the default is blocking offload, is there an option for asynchronous? So I think that question has been superseded by one of my last slides. So yes, there is the option to be asynchronous. It's just that we kind of reversed it, where CUDA and HIP and also OpenCL assume that you're asynchronous by default. In OpenMP, the default is synchronous, and you have to turn it to asynchronous. But yes, that is supported and is working. Okay, could you talk a bit about the new loop clause? I already mentioned it. So the idea here is that instead of prescribing teams distribute parallel for SIMD, you basically tell the implementation pragma target loop, and then the corresponding binding, and then the implementation would figure out how to best map that loop using distribute parallel for and SIMD to the underlying GPU. And the idea really is that you get high-level descriptive parallelism by just telling the implementation, here's a parallel loop, and please, dear implementation, go figure out how to best map that loop on a particular hardware architecture. Then there's a question, can I explicitly control the lifetime of the variables in the device? I don't want to guess whether the compiler checks the data presences. That is, yes, you can explicitly control the lifetime. I showed you a bunch of cases where this was done. You can obviously also use the low-level API routine, so you can use an OpenMP target alloc to explicitly allocate a buffer, and then you can use OpenMP target free to release it. And in between, you can use OMP target memcopy operations to move data around if you want absolute and explicit control over that. Other than that, if you use the directives, you basically have to learn about the rules when a data transfer will happen. And so you then have to keep kind of a map or the information in your context of the offload kernel to know if something has to be moved over or not, and if the implementation will actually do that. And if you're unsure if it's actually happening at runtime, then we can go back to one of the first and earlier questions, where you can use a tool like rocprof and vprof or some environment variables that are coming from the implementation to get like a performance profile out of your execution to see when and how data transfers are happening. Then there is a question, is there support for sort of a stream as CUDA does? A dependency not only related to data, but related to some tag that I assign to some kernel. Yes and no. No, in the sense that we don't have this explicit restriction that if you do two asynchronous kernels from the same thread, that they have to execute on the same underlying GPU stream. Yes, in the sense that we have dependencies. So you can mimic the relative order of the asynchronous offload regions by introducing dependencies, and then the implementation has to ensure that they're executing in the right order, but still you don't have the guarantee that this is actually happening on the same stream. Now, the thing that I said as part of the summary, we do have a feature where you can actually ask OpenMP, hey, what's your default stream that you're sending offload kernels to? And so you can pick that and get that underlying stream object and start enqueuing into that same stream if you wanted to. All right, then a question, why is that all accelerators must be of the same type? There are two reasons. First of all, sometimes it's just vendor politics, right? So it's sometimes hard to convince one vendor to provide a GPU compiler for another vendor. Now with Clang being adopted throughout the community, that kind of is a weaker argument, to be honest. The simple reason is that up to this point, we did not specify how you can actually reason about which kind of device you are targeting. This is something that we're talking about to have in OpenMP 6. So the idea is, up to now, you only have 0 to n-1. That's kind of the ID that is attached to your GPUs. And you can't get anything out of this, like if this is a NVIDIA GPU or an AMD GPU. That is just not part of the OpenMP language so far. There are implementation-specific mechanisms and operating system-specific mechanisms how you can find that information, and then build your own map that GPU 0 is an NVIDIA one, GPU 1 is an AMD one, for instance, right? But OpenMP doesn't have a feature for that. With OpenMP 6, what we will do is we will actually have mechanisms so that you can say, give me the IDs of all the NVIDIA GPUs of the system, give me all the IDs of the AMD GPUs of that system, and then you can actually get that information out of the system and then send to specific GPU architectures. But that, in parentheses, will require an OpenMP compiler that will actually support both NVIDIA GPUs and AMD GPUs in the same binary. So that's kind of a prerequisite. All right, related to this, it would be nice if the offload part can be encapsulated in a task on the host. I can then use a task dependence to schedule other work on the host around the offload. Yes, that was how it had to be initially done with OpenMP 4.0. With OpenMP 4.5, we then introduced the no-wait keyword or the no-wait clause for target directives. The downside, though, of that approach that is quoted in that question/comment is that you actually lose the host thread that is doing the offload, right? So you can nicely wrap a synchronous target directive in an OpenMP task that you then run on the host thread. But while that offload region is running on a GPU, that task will stay on that executor thread, and it will block that executor thread from executing other tasks. So in that regard, you can do it. It was a good workaround until 4.5, but the ultimate way is actually to use the no-wait clause and task dependencies and task synchronization construct to get a much better working solution. Is there a way to directly copy data from one device to another device without going through the main memory? Not really. OpenMP assumes that at least it assumes that the OpenMP target mem copy is executed from the host. And then if you do a device-to-device copy, it is then an implementation question whether they will route the data directly between the GPUs, whether they are going through the host. So this is, again, a quality of implementation question, because that is really implementation defined. OpenMP does not make any assumptions of the fabric between GPUs and the host, except that the host can talk to GPUs. Okay, is it true that we can use one of the cores as a GPU, or that's not implemented yet? Well, not really that use one of the cores as a GPUs. I read this question to be related to the host fallback. So I mean, there's the host fallback, and that would parallelize if you have a parallel statement in there. So it would actually not only use one particular core, but all of them that are available to the OpenMP process and that are free to execute. All right, and we are way past the hour, I think. But I'll just keep going answering questions, because we have two more left, maybe. Yes, two. All right, how do you think of the OpenMP target model with respect to data analytic workflow needs? That is a very generic question. Not sure how to answer it, actually. I mean, I think we do have the right building blocks so that you can move data over as you need it for that workflow. Related to the previous question about tensor cores and metrics operations and that kind of stuff, again, this is a question for the implementer to have a compiler that is actually able to analyze and see if you have convolutions or tensor operations, and then use the appropriate underlying low-level hardware infrastructure for that kind of operation. So I think in theory it's possible. It's not that we specifically designed it. If you feel that we have a lack in OpenMP there, please feel free to take one of the user conferences that I advertised, or IWAMP. Or since this is actually coming from somebody who's at least indirectly associated with the ARB, looking forward to a proposal here that we can discuss in the language committee to potentially include it in OpenMP 6. All right, final question. If I map some data which is already on GPU, will the data mapping clause be executed or ignored? It will be executed, it will not be ignored, but the effect will be that it's kind of the next level of details, but because you're asking for it, there's kind of a reference count attached to a GPU buffer. So it will certainly not move the data over again, but what it would rather do, and so that's why it's not ignored, it will increase the reference count, and then when the region ends, it will decrease that reference count so that OpenMP internally can keep track and tally of how many times data has been mapped before, and when the reference count actually reaches 0, it will release that GPU buffer. There are actually ways how you can influence that, but that is way beyond an introductory example or an introductory webinar. So for the question, look at the always modifier for a map clause, where you can control whether you want the data to be always be retransferred, if you will, or if the map clause should be ignored except for keeping the tally. All right, that was my last question. Thank you for attending. I'm done. Thanks for staying 30 minutes longer than anticipated. And I'm handing now back to Lizzie to close the webinar. Thanks for listening. Appreciate it.
Thank you, Michael. That was a great presentation.